Welcome to Module 44, in which we talk about convolutions. We're going to see pooling, as we've seen before, but we're going to see it in the context of convolutions, and CNN architectures. CNN architectures are really going to be the topic of the following module, but we're going to just touch on them a little bit today. So by the end of this module, you ought to be able to explain what a discrete convolution layer does in a neural network in terms like receptive fields, weight sharing, and equivariance, at least equivariance to translation. You'll be able to derive and manipulate a few basic convolution hyperparameters. You'll understand what's called a kernel size, a stride, padding, and channels. We'll introduce all of these ideas today. You'll be able to compare and implement different pooling strategies, at least at a very high level, and you'll be able to reason sort of on how well they have an effect on invariance and so on. You ought to be able to compare a small convolutional neural network architecture, or CNN architecture, for the purposes of image classification. We're going to see a whole worked example just introducing this idea, and you'll be able to compare it against a good old-fashioned multi-layer perceptron. And in that comparison, you'll be able to look at training curves, accuracy metrics, and again, evaluate and diagnose training through the familiar terms we've seen several times before, specifically underfitting and overfitting. So we're going to mostly get into the idea of computer vision. So in computer vision, the idea is to do some sort of inference and then therefore training given images. And images can come from just cameras, like they're photographs. They can be frames of video, or they can come from some other sort of imaging. But the idea is we have this two-dimensional data that more or less takes the form of an image, a photograph. So here we have a couple of very simple examples. We have a grayscale image. A grayscale image is a two-dimensional matrix of just intensities. So there's a height, h, which is the number of rows of pixels. There's a width, w, which is the number of columns of pixels. And then you have the value of every pixel, which is just the intensity, from like no intensity, which is black, to full intensity, which is white. Normally photographs have additional channels. So you'll have a red, a green, and a blue channel. So again, you have an image which has a certain height, a certain width, but now every pixel is represented by three scalar values. It's redness, it's greenness, and it's blueness, or it's red intensity, green intensity, and blue intensity. Generally, a deep learning library will have also, it'll care about the batch size. We introduced the idea of batch processing. Given a lot of training data, you only look at a small batch at a time. And that batch will have a number of images in it. We'll call that batch size n. And then in general, you can have a more varied channels. So we can have one channel for grayscale images, three for simple RGB images. You might have like an alpha channel for transparency. That's a fourth channel, so COB4. Other imaging techniques might have many more channels or fewer channels, but that's generally something we have to deal with. The key insight now we have to think about is that in images, nearby pixels ought to be very highly related to one another. There's a lot of structure in images that we haven't had to deal with too much when our inputs were just sort of variables that were interchangeable. Like the variables we saw in spreadsheets, for example, the columns could be swapped around without any loss of information. But in photographs, say, if you were to just shift the camera over slightly, or indeed to rotate it, or also if you were to just move the objects in the scene slightly, you'd see a massive change in pixels, and all of those pixels would change with each other. Okay, that's a kind of crucial thing to remember. I'll get back to this in a second. But the idea is that if I'm looking at a keyboard here, you can't see this, but if I take a photograph of this keyboard and then just move it over half a centimeter, the general pattern of pixels over my field of vision will, like the keyboard will stay the same. It won't, its shape won't change, its color won't change, its texture, and so on and so on. The relationship between the keys won't change, but all of the pixels in this little range will be different given a slight motion to the left, to the right, or whatever. Okay? It doesn't change the identity of the object. It doesn't change what I'm trying to predict. If I'm trying to label the scene as there's a keyboard in this scene, That won't change. So I need a kind of an architecture for neural network learning that exploits this locality, the fact that nearby pixels should change together. And similarly, that if I were to move the camera over slightly or the object in the scene slightly, because of this locality, there should be an invariance to my representation of the scene. So, I mean, so far we've had multi-layer perceptrons, sometimes a lot of them stacked on top of each other. And, you know, if we had an image, we've seen this previously with digit recognition, we would take the image and then we'd flatten it. We'd take, you know, all of the rows and then just, you know, put them into one long vector. So if you were to have a 32 by 32 RGB image, you'd flatten those 32 by 32 pixels. Every pixel would also be represented by 3 scalars. And this translates to over 3,000 input features. So the input for a neural network has to have about, well, 3,072 features. For this size of input, a hidden layer with 512 units is reasonable. You know, it's a bit smaller. It brings in some representation. So now, how many weights are we going to have between 3,072 inputs and 512 hidden units? Well, this is about 1.6 million weights. Okay, which is not huge by today's standards, but just for this very simple problem, it is pretty large. You know, so getting ahead of myself a little bit, you know, this, I say huge here, huge relatively, number of parameters means that the same old problems will occur. It'll be slower to train because we're going to have to train all of these weights. We're going to need more images to train all of these weights because of all the variations that can occur in real data. We're going to need many, many more data points in order to learn anything reasonable. And of course, the more data points we get, you know, that has an effect on whether we underfit or overfit. And, you know, in reasonable circumstances, if you have a ton of parameters like 1.6 million weights and a reasonable size of images, a reasonable amount of images, then again, the old specter of overfitting rears its head. So all of the locality I mentioned, you know, the fact that there's edges and there's relationships in the scene, there's corners, there's textures, this kind of goes out the window when I've kind of flattened an image and nearby pixels will be separated and will be kind of distributed out through the input layer. So we actually aren't taking into any kind of spatial structure. So pixel 0, 0 and in the upper left-hand corner and pixel 31, 31 in the bottom right corner are treated similarly, and there's no structure in our neural network that's telling us that these should be very far from each other. There's also no structure saying that pixel 0, 0 and pixel 0, 1, the pixel right next to it, are next to each other. They're just, like the weights can't see that. It's just a fully connected you know, layer. It's a matrix of numbers, and any kind of structure that exists, that we know exists, will have to be learned from the data. And that's going to be extremely challenging. Again, because of translation, imagine if you've trained an image recognizer on digits that have all been centered. So all of the digits that are drawn in our data set, the center is in the center of the image. But imagine for some reason, like realistically, you have a digit drawn, but it's shifted over by 1 pixel. So its center is just 1 pixel over from the true center of the image. You know, even given a ton of data that we'd need for this setup, you might not have any images that have digits that are just centered over by 1 pixel from the true center of the image. And the neural network trained under those circumstances will have no idea that this 1, which looks exactly like a 1, is a 1 because it's never seen an image before where its center is centered in the is off the center of the image. This is kind of a contrived example, but hopefully it gets across the idea that any kind of translation of obvious objects will not be obvious to a neural network that just hasn't seen that kind of variation before, and that will cause accuracy to drop sharply. So any kind of high-level semantic information will have to be learned from scratch entirely. So here we have kind of the big picture of a convolution. And you can see it here. So on the left, we have this image. It's a grayscale image, I guess. Every pixel here is just represented by a single number, its intensity. And then we have this 3 by 3 little grid, which we call a kernel or a filter, which is the crucial sort of innovation of a convolutional neural network. And in this case, every number in this filter is a value that can be learned, and we're going to kind of skip over like exactly how that is, but just like every other parameter that we've seen in neural networks, these numbers can be learned. And what we're going to do is we're going to, for every position it's in, it'll be centered over a particular pixel. Then we're just going to take a linear combination of all of the pixels in its range with its value. So here in a moment you'll see what I'm talking about. It's like 7 times 0 plus minus 1 times 7 plus 0 times 6 and so on. And you add all of this up and it gives you 9, and this is the output of the filter over this part of the scene. And then you can just shift it. So we're going to shift the kernel, as you can see right now, centered over every pixel in the image, kind of as a sort of a scan. And we're going to do the same kind of linear combination, and it's going to give us a different output, which we'll put into this other 2x2 grid, which will be sort of the output of this convolution. It's a modification of the original image, or signal, I guess you could call it, by this function, which is this kernel filter. So we're going to reuse the same weights. So the same exact weights in this filter are going to be used in this scan across the entire input. So we share this information. We don't have to learn something new from scratch every time. And then again, we have this feature map at the end. So this is intuition. This is very high level, but we can learn this. We can learn a filter here to do almost everything. We can also specify by hand if we wished. The idea is these filters can represent some high level, but still local information in the image. So down here, I mentioned a couple of them. It could be an edge detector. We'll see an example of this in worked example 1. This filter can basically respond very highly to an edge which is horizontal, which we'll see later, or maybe a vertical image, which we'll see later. But similarly, this filter can represent blurring or smoothing. It can represent texture, so it can give a very high value to a very smooth image or a very highly textured image, and we'll write that information into our output over here. Also, you don't need to have just one kernel working at a time. Given an input image, you can have a couple of different kernels, all scanning over the same image, all giving different outputs to the next layer out here, the activations. And so simultaneously, you could measure the edges in the raw image, the texture in the raw image, curves in the raw image, the intensity overall in the overall image. So anything your heart desires, can be represented by a number of kernels applied on the image and producing a number of output layers in the output. Let's go into the math a little bit. So where does convolution come from? It kind of comes from digital signal processing. In digital signal processing, we have the idea of an input signal, X. Here, the input signal is one-dimensional, like it's a time series, but it generalizes to 2 dimensions like images. And then we'll have a filter or another function W, which is a kernel. And the discrete convolution is defined like this. So you're going to shift the input function X by a certain amount K. And K can be -1, -2, -3, like frames or indices. And you're going to multiply it by the filter or the kernel W. And you're just going to sum up over all of these values. And then this will give you the convolution Y. As a side note here, often people, when they're trying to talk about multiplication between 2 numbers, they'll have like variable, asterisk, variable. And to a mathematician, which increasingly you are, you'll see an asterisk and you'll be like, well, like that technically shouldn't be an asterisk when you're just multiplying 2 numbers together, because technically an asterisk should be reserved for convolutions of this type. And then you can be pedantic to your friends and neighbors and annoy them with that bit of trivia. But anyway, this asterisk means convolution, and it's supposed to really be nothing else. Here you can see what a convolution looks like. The filter, in this case, is called F, which we called W over here a moment ago. In this case, it has this sort of shape to it. It has this, it kind of just tapers off from an initially high value. And then you have a function, G, which in this case is just a boring old square function, but you can see how you kind of scan it over the filter. In this case, the filter stays still and you scan the image or the signal over it. And when you multiply them together, you get the convolution, which is basically the area under them, which is this black curve you see over here. So high level, if this doesn't make too much sense, and hopefully it makes a little bit of sense intuitively now, a convolution is sort of just the product of a filter, which we can define in different ways, and then the input kind of scanned over the filter. And there you have it. In deep learning libraries of the kind we're going to see a bit later, technically it's something called cross-correlation instead, and cross-correlation, also to be pedantic, is represented by the star operator. But it's basically the same thing. The only difference is instead of subtracting the offset k, we add the offset k. This difference really doesn't matter to us. It's the same general idea. So, I mean, again, if you want to be pedantic and some machine learning person talks about this function as if it's a convolution, you can be like, well, actually, it's a cross-correlation, but then, again, that's going to annoy people more than anything. So for a single channel, two-dimensional input, like we care about 2 dimensions, we have our image x. This is a real valued sort of grayscale image, say, with height times width, and we'll have a kernel function, which has its own height and width. I'll say the height of the kernel is k sub h, and the width of the kernel is k sub w. Can I zoom out? I sure hope so. Good. The convolution is defined thus. Like, this is essentially the same function we saw before. It's just that instead of summing once because we have a one-dimensional signal, we sum twice because we sum over the heights, the rows, and we sum over the widths, the columns. Okay, but the same general idea. We multiply the kernel at that point by the offset input. So here's just an example, if it's not clear. This is our raw image. We have like a 5x5 image over here. And then we have a 3x3 kernel, which is right at this point in time centered over this center row 2, column 2. But that down here, I'm kind of counting from the lower left-hand quadrant, but this generalizes. So the kernel function is this weird-shaped plus thing. This plus responds positively to these kind of medium blue pixels. It responds very negatively to the center pixel, and it responds like with zeros in the corners. You can do this yourself. So unfortunately, to some extent, the product here is kind of boring 0. So if we have an intensity of 11 times 0, that's 0. Like all these corner pixels multiplied by these kernels, as we kind of fit the kernel over the image, will all go to 0. Then we have times 1 for each of these pixels, 12, 10, 6, and 8. So adding all those together should be, I think, 36. 9 times minus 4 is minus 36. When you add all of these together, you get 0. Hence, the output of this 3x3 kernel, centered right for this moment in the center of our 5x5 image, will give you a 0 of output. Okay, so a little bit boring, but hopefully this gets the idea of just the image input x multiplied by the kernel gives us an output, as seen here. So we have hyperparameters. We always do. We always have to contend with them. And so I mentioned a moment ago, we have the height of our kernel and we have the width of the kernel. And normally we use squares. It doesn't have to be, but just by convention, these are the same. And then we have a stride. So I'm assuming I'm moving 1 pixel at a time, but I could move 2 pixels at a time. So for every step, I could jump over a pixel, and my stride would be 2 in that case. And then I also have padding. I didn't really mention that before, but you can imagine if I wanted to center my kernel at the corners, like not always the kernel, but definitely the kernel. If I say that again, if I wanted to center my kernel at the corner of the image, then parts of that kernel will fall over the edge of the image and will not overlap the image that I'm trying to scan over. So padding basically just allows me to say how many pixels I'm going to add around the border, and normally this is going to be zeros, and this just allows us to move the kernel to the actual corners of the image when I'm doing my scan. You'll see some visualizations of this in a moment. Just for completion's sake, we'll have the h out and for height and the w out for width are now going to be the floors of the same kind of function. We're going to have to deal with the stride and the SSH and the padding P of h in each of these cases. And you have to take the floor of all of these. This is kind of detail that you're not going to need to know later. But just for intuition, I want to show you these images, which gets it across. You can see in this upper left-hand corner, there's no padding. So when I'm scanning my kernel over my image, the kernel here is this green 2 by 2, and the image is this blue 4 by 4. If I have no padding, the kernel can only fit, in such a way that the kernel's upper left-hand quadrant is in the upper left-hand of the image. See there? And I can only have these kind of smaller number of spots I can walk over. Sorry, the kernel is actually a 3 by 3 kernel. So this green area here is not the kernel. This is the output of the kernel. So the kind of shaded region down here represents the kernel. This kernel does not overlap at all. Over here, I have a padding of 1, and now you can see when I'm moving over the image that I still have a 3 by 3 kernel, but now the kernel has a padding of 1, which means that I can move it to the edges and the corners of the image, so that I can now center over each of the pixels in the image. There, for example, and there. All of these areas of the kernel that are not over the image, like on the slide over here now, are just going to be 0, so I can kind of ignore those non-pixels that are not part of the original image. But what I get now is I get a nice 5 by 5 output, which represents, in some sense, a kernel centered over every single pixel of the original image. The two visualizations down here show, again, 3 by 3 kernels, but now I have strides of 2. So if you can quickly see here, like I'm jumping over a pixel in each case. So first I have 0 padding, so the kernel can't hang over the side of the image. The first kernel has to be centered where I'm indicating right now, there, but then I jump over the central pixel, and now my kernel is centered at this pixel right there. And then I have to go to the next row of the image, so again I have another 2 by 2 output activation of this setup with hyperparameters for, like again, the kernel height and width are 3 in each case, and then I can adjust my padding and stride according to, you can see here, so padding and stride are 2 other hyperparameters I have to deal with. So for multi-channels, I don't just have these. See, I've zoomed in again, haven't I? Can I hopefully do this without breaking? It'll have to do, I think. Yeah, so instead of having just like a real valued images of scalars, now I have to deal with a number of input channels called Cin. So if it's an RGB image, Cin is 3, and my convolutional filter is going to have weights over each of those channels. So I'll have a say case of H is 3, case of W is 3, because I have a 3 by 3 square that I scan over the image, but then every pixel has to be represented as 3 intensities in Cin. So everything is essentially the same. I'm still going to have to sum over U and V for my rows and columns of my image, but now I also have to sum over each channel that I have available to me. Again, if I have a 4th channel for alpha for transparency, Cin will be 4. The same idea. I have a kernel with these 3 variables, and again, you just multiply that by the input, offset by U and V respectively. So to produce a output filter maps, I can actually use a different number of filters. I alluded to this earlier, so I don't have to have just one filter that or kernel that looks over an input image and say detects horizontal edges or vertical edges or a certain kind of texture or a certain kind of intensity. I don't have to choose. I can have a ton of filters scanning over my original image, where a ton would equal C sub out. Okay, this is yet another hyperparameter that you have at your disposal. So now you have this complexity where you have this weight tensor where, say, I'll have a bunch of 3 by 3 square-looking kernels that I'm going to scan over my input image. Each entry of my kernel is going to have Cin channels. So if it's RGB, Cin would be 3. If I have the 4th channel, Cin would be 4. But now I'm going to say, well, I want to learn 16 filters that I'm going to scan over my image. Then C out would be 16. Okay, and then all of these kernel values, which so far again I'm treating as if they're fixed, will be the weight tensor that I'm going to have to learn at some point. So my weight tensor W is in this very increasingly high dimensional space. Here's an image just to kind of hammer home the point that I'm trying to make with regards to different filters doing different things. Again, this is a cartoon example, as you see constantly in machine learning educational material such as this. Imagine you're trying to build a smiley face detector. And in red here, you have the raw inputs, which is maybe binary. So all of these red pixels represent 0, and these purple ones represent they're 1, they're active. So you might have a 3x3 kernel function, which basically all it's doing is learning the edges of the smile, the upturned edges of the smile, and you're going to scan this particular kernel over this entire image, and it's going to respond with no value if it detected nothing that looks like a upturned mouth, and it'll return something like 1 if it does. So in this case, you can see it's sort of being scanned over this image, and in this little quadrant over here, this area of the raw image, it finds nothing, so it outputs nothing. But if you were to scan this particular kernel down here near the edge where this upturned smile does occur, it'll be, oh, I found the thing that I'm looking for. I found kind of an upturned edge of a smile, and it'll respond positively when it's writing out its output two-dimensional pseudo image for further processing. Another kernel, like this one over here, might represent eyes, which are just maybe single dots surrounded by nothingness. So when you're scanning this kernel over the image, it'll basically respond with nothing, but then when it's centered over exactly what we're looking for, it'll respond positively, and we'll write out outputs, in areas where eyes ought to occur. And similar, we'll have like the bottom of the mouth, a kernel representing the bottom of the mouth, or an edge representing the bottom of the mouth will respond positively to this little area of the image, and then it'll write out that output to its layer. So instead of having a single output layer of neurons for a single overall layer of the neural network, you're going to have multiple layers all kind of stacked on top of each other at this particular layer of the neural network. Okay, so this can be seen as one layer. Its input, in this case, is the raw image. Its output is the amount of upturned smiles, the eyes, bottom parts of the mouth, and for each of these slices here, we're going to have a different kernel. These different kernels are counted by C sub out. And then we're going to learn all of this. So again, like all of these values here, which are just right now cartoonish -1s and +1s and -2s. All of these values, like I'm indicating over here, and these kernels are going to be things that we're going to learn through backpropagation. Not necessarily always backpropagation, but for now, that's what it is. So how many parameters are we going to have to learn? So going back to our 32 by 32 RGB images with 3 channels, because of RGB, we have 32 rows, 32 columns, and for now we're going to say we're going to have 64 hidden units. A good old-fashioned multi-layer perceptron will have to have, like we mentioned earlier, 3,072 inputs, and with 64 hidden layers, or input layer neurons, we're going to have almost 200,000 units, plus we're going to have 64 biases. Every weight comes with a bias. Our convolutional layer now, imagine we have one kernel, size 3 by 3. It'll have a stride 1, padding 1. So it's one filter. So the kernel is 3 by 3, but it has 3 channels. So that will be 27 weights we're going to have to learn. We're going to have 64 filters that we're going to pass over the image. And this will give us, sorry, take that back. We don't have one kernel, we have 64 of them. Okay, so we're learning 64 different kinds of aspects of the image. So again, a moment ago we had 3 kernels, 3 little functions we're learning. Now we have 64 of them. So even in this case, again, and that we're going to scan over the entire image. We're going to have padding of 1 and stride of 1. So we're going to center this 3 by 3 kernel over every pixel of our inputs. So we have 27 weights for every kernel, 64 kernels. This is 1,728 weights, plus we're going to have our biases. And that's it. So discounting biases for the moment, we'll have almost 200,000 weights we're going to have to learn in the standard multi-layer perceptron, but fewer than 2,000 weights to learn in the convolutional neural network. That is learning kind of 64 features for us. So, it's hard to tell what effect this is going to have. We're going to have to do an experiment to see if this difference of several orders of magnitude in terms of fewer weights in the convolutional neural network is going to be meaningful for us. But so far, it seems that not only is these convolutions learning a little bit of very local structure, which was something we wanted, but it's doing so very efficiently. A little bit of math here. So again, this is one of the aside type things. Imagine you want to shift the input. So I'm shifting my keyboard on my desk, or you're shifting the camera over a little bit. The feature map that we're learning, all of these updates to our kernels that we're learning, will have to ideally shift in the same kind of way, so that we're not going to have to learn everything from scratch for every slight deviation that will obviously occur in real life. So let's, for a moment, to simplify and imagine one-dimensional signals like we saw earlier in our cross-correlation. So we have our input, x, we have our kernel function, w, and we have our output, which is the cross-correlation, which is represented this way, like we mentioned at the very first slide. Imagine we have a shift operator t, which is going to just shift all of the pixels in the image by some factor delta, and that's it. So it's just going to take x, and it's going to shift over every pixel by this factor delta, as you can see here. So our claim, what we want, is that the so-called convolution of the shifted input x with our good old weight kernel w will be just the same thing we'd expect if we shifted the convolution by that amount delta. In other words, like whatever y was going to be, y, the output of our convolution at point I, will also just be shifted by delta. That's kind of what we want. That's equivariance. That means that we're like, small changes to the input will result with basically the same changes to the output. So again, this is something you're not going to need to prove anything in the assignments or anything, but for completion's sake, I think this is important because equivariance, the translation, is one of the fundamental factors of convolution. So here, as walking through it, we have the translation of the input applied to our little so-called convolutional function I plus k. T, the translation of x as it's defined here, basically just adds this minus delta. So here we have the update. We can move things around a little bit. This is the same as I minus delta plus k. And if we just redefine a new variable, I minus delta, then the translation y of, say, u is going to be this function, but I is replaced with a u. If u is equal to I minus delta, then there's no change, and then we get exactly what we're looking for. We replace u again with I minus delta, and what we get is down here, which is what we're looking for. This is not so much of a proof as something that's, I guess, relatively obvious. But yeah, like if you translate the inputs by a factor delta, then the outputs of your convolution, so-called convolution, will be just a translation of the outputs by the factor delta. So all we're doing is kind of shifting variables around in this little kind of input to x, but it's great. So directly we get the idea that if we shift the inputs a little bit, the outputs will shift the same way. And what that means is that we don't have to provide examples of every possible translation of our inputs, because the convolutions that we're passing over, the filters that we're passing over our inputs, are going to be resistant to those kinds of changes, which is one of the fantastic things we wanted to gain over good old-fashioned multi-layer perceptrons. We can also do pooling. We saw pooling before as sort of a form of regularization. So pooling layers can reduce spatial resolution, and it can kind of sum over local neighborhoods. Sorry for the spelling mistake. Nobody spells it this way. So max pooling basically says, well, like whatever, like when you're moving the kernels over a particular space, you'll pick whatever the maximum is in this window, and then that will be the output for this kernel. So this basically gives you the strongest activation. Instead of taking the weighted sum, you'll take just the strongest activation. This will encourage local translation invariance, so small shifts of an edge will still give you a high response, regardless if that high edge is in the upper quadrant or the lower quadrant. It doesn't matter. So taking these maxes, it's extremely common. I think it's extremely common partially because of precedent. Lots of other people use max pooling, so we're going to use max pooling too. More importantly, it tends to give you good results if you use max pooling empirically, but it doesn't necessarily guarantee that you'll always get better results if you use max pooling, so it's always good, as I keep on trying to emphasize, to do the experiments yourself. Average pooling, as the name suggests, is just sort of an average over all of these applications. So for every U and V in your filter W, you have your X, you have all your shifts, U and V. You'll basically get the average of all of these, and this is going to be your output Y. This is smooth. It'll preserve averages, as the name suggests. It'll again, as the name suggests, it will smooth things out because of averaging, and it'll reduce sharpness, which sometimes can be a good thing. And again, pooling window size and the stride, often those are hyperparameters. The same kind of caveats exist with regards to them. They'll still control how much invariance you get. They'll still control how much downsampling you get, like we saw before in the grid of animations with different strides and like overlaps. But you'll again, these are hyperparameters, so you need to do experiments to figure out which ones are best. So let's take a quick anti-example. We're going to want to use CNNs to recognize digits, like we've been seeing before. We're going to use max pooling. We're going to have window sizes of 7 by 7, so fairly big kernels. And we're going to stride by a whole lot. We're going to take jumps of 7 at a time. And after a few of these, so these big blocks of convolution and pooling, we can stack them on top of each other, just like any other good neural network. And then pretty soon the feature maps will be very tiny. They'll be like 1 by 1 little pixels, which at the end, I guess it's not the worst thing in the world if you're doing binary classification. But because of this big kernel and this big stride we're taking, these windows are going to collapse lots of different inputs into one pooled value. We're doing max pooling over a big window, so we're going to take a max over many pixels. This will kind of be a summary, which will discard a lot of information. And that's the key idea. The network's later layers will see the same representation no matter where the pattern appeared. Okay, so if the pattern appeared in the upper left or the lower right, it doesn't matter. It'll see the same exact output because of this pooling that we're doing. And the consequences are the model will be, invariance is good, but being too invariant is bad. So being totally invariant to location, like if we're summarizing and ignoring like true location in these big windows, where the stroke is drawn won't matter anymore. So zooming out, whether the eye is above or below the happy face for a happy face detector will be lost. So also distinguishing between fine local structure, like the small differences between a 3 and an 8 or a 6 and a 0, that'll be lost. And then training may saturate at some point, but then tests accuracy will suffer. Like the model won't have learned any of the useful variance or the useful discriminating information, so you're going to get bad results. If you have the time, you can set up this experiment for yourself. In fact, it won't be too hard. We've seen a lot of digit recognition in previous modules, and you're going to see a lot of examples of CNN from this lecture. So you can make the windows big, add max pooling, make the stride huge, and you'll see similar kinds of consequences that I'm describing. So pooling is powerful. It works well in practice, but again, don't put all of your eggs in one basket. And just because invariance, like we've been searching for since the beginning of this module, is good, too much of a good thing leaves you wanting less, as they say. So let's see some examples for initially edge detection. This won't be the most exciting example, I have to warn you, but hopefully it gets the idea across. So we're going to have a toy case. We're going to have a tiny, quote, image, which is shown here. It's a grayscale. So again, you can get the code and you can just run it yourself. So it's basically like it's a 5 by 5 image. It's black everywhere except there's like a big white line in the middle over here indicated by these ones. This is our image. We're going to have a kernel. Well, here's the object detecting kernel. It's going to have three. This is kind of like the ugly thing we saw before. It's going to be positive on top, negative on the bottom, and zeros in the middle. Basically, this is essentially a kernel that doesn't say I'm in the middle of a edge. What this kernel is detecting is there's an edge underneath me. I'm right on top of an edge at the bottom of my bottom pixels. And again, this is given to you, but you can tweak this this kernel and to be anything else you want to see how it responds. You can try to swap things so to make this a vertical edge detector. But here is basically where I do the convolution. You can see this is the input image we saw in the previous slide in table form. It's all black with edge in the middle. Applying a convolution to this input image gives you this response, and this response is basically telling us with this high value output, which I'm indicating right here, this white pseudo pixel says there's definitely an edge right below me. And actually this grayish edge in the middle still responds well to being an edge where I am. So this is my edge detector. I can have pooling, so I can have max pooling over 2 dimensions, so I'll have a pool size of 2 and a stride of 2. Actually, sorry, the default is a stride of 2, but I'm using a stride of 1 for this experiment. And I get this response. Because I'm pooling over 2 by 2s, I get this response over here. So this is the response of max pooling, and then this is a visualization of the max pool, a max pooling over the convolution that I performed a moment ago. So image, pass through a filter that gives me the activations that are the output of my block. This is the after the convolution. But just like we saw previously with pooling in good old-fashioned feed-forward neural networks, I can apply a pooling here. In this case, it's the max pooling over this image with a pseudo image after convolution, and then this gives me this this output here. So this is getting pretty coarse. So I mean, I'm not gaining too much here, but I am getting a pretty strong response suggesting that there's definitely an edge, and it's somewhat below the very top of the image. Okay, so this doesn't have to respond directly. I mean, quite frankly, like the original image is a pretty good indication of where an edge is, but this being fed forward to a neural network will tell some output layers that are attending to this top row of the pool that there's an edge in this image. So pooling kind of stores where the edge is in a very coarse sense. So I'm still kind of like, I still know that it's below the top part of the image, but as I'm passing my convolutions through this pooling, I'm getting coarser and coarser. In fact, I'd like you to go ahead and experiment with this pooling and see what happens if you set the stride to 2, and the response will be indeed even coarser than this, because we're taking big jumps over the image. You'll get a 1-by-1 output in that case. So the receptive field of a unit is essentially how much of the region it sees. Oh, there I am again. Hopefully I can do this without breaking anything. Excellent. Good. So imagine you have a 3-by-3 convolution layer with stride 1 and no pooling. Every output pixel will depend on a 3-by-3 patch of the input, like we've defined it before. And then you're going to stack another, again, 3-by-3 convolutional block on top of the outputs. Okay, so to keep that as a visual, this is a 3-by-3 kernel passed over this image, and then this will give me this output over here. If I have another kernel after this block, a second layer of neurons, second neural network block, on top of this layer, it'll essentially see a 5-by-5 region of the original image. I'll show you a visualization of this in a moment if it's not clear, but the first layer will just see 3-by-3 pixels, and it'll move over it'll scan over the raw input, but it'll produce another 2-by-2 grid, essentially, that will look like an image, right? I'm ignoring things for the moment like channels and number of kernels, but for the most default case where I have one kernel and I have this one channel, imagine the kernel moving over an image, producing another pseudo image as output, like we've seen several times in this module. And now imagine there's a second layer which has another kernel, another 3x3 kernel, looking at that at the output of the first layer kernel. Because every point of the output layer represents one location of the scan in the first layer, when I'm looking at the image, the 3x3 image in the second layer, I'm looking at multiple positions of that first kernel in the first layer of input, the two-dimensional image. This will hopefully make sense. I mean, hopefully it makes sense now, but it'll make more sense when you see it, I think, for most of you. Imagine now that we have pooling, we have stride of 2, the receptive field will grow. If you're striding over a lot of the image, the receptive field will be bigger. Here's another example. So we'll have one layer, which is a convolutional block, which has a kernel and maybe a pooling layer. And then that will produce another layer of outputs, which will look like inputs to the next layer, which will be conv2, the next block. This also has a kernel of size 3x3, like I mentioned a moment ago, a stride of 1. I mentioned there'll be a 5x5 effective size. And I'll take a max pooling there, a 2x2 over that, so this will be basically a 6x6. It'll be coarser after the pool, but it'll essentially see a 6x6 image in terms of the raw pixels. So each of these numbers in the last column refer to how much this higher and higher level kernels or layers kind of see of the overall image, to the point that you expect as you stack these convolutional blocks on top of each other, at some point the convolutional block will have received information from every corner of the original image, potentially. Here's just a visualization of what I'm talking about. So here's the first layer, which is like the raw pixels of an image. It's passed through a first convolutional block. In this case, the convolution will be a 3x3 kernel. So you can see here, there's this little shaded region represents the 3x3 kernel, and it will write its value to this shaded region here in the second layer. This is the output of the first convolutional block. Okay, and then if I move this kernel over, like I'm going to do, I'm going to scan my kernel over the entire image. The next center will be over here where my mouse is. It'll essentially see these 9 pixels at this point in time, producing this pseudo pixel as output. Okay, and then the next one, centered where I'm pointing the mouse over here, we'll see this 3x3 region. It'll write to this pixel or pseudo pixel over here as output in the first convolutional block. So that's the first convolutional block. But now I can stack things. Like the great thing about neural networks is you can stack things. At the next layer, I have another 3x3 kernel, which doesn't take the raw inputs of the pixel of the original image, but it'll take the pseudo pixels of the outputs of the first convolutional block. And here it is. So, when I'm looking at this kernel, which is now just the colored region in the middle over here, this will see this input to this kernel will basically be the output of the previous kernel that saw this 3x3 region. The input to the kernel in block 2, which I'm indicating over here, will basically received all of the information from all of these 9 pixels from this kernel in the first convolutional block, and so on and so on and so on. Okay, so in fact, even by this point in the second layer, this kernel will have received information from all of the pixels in the original image, but filtered through these kernel functions, such that at the end here, like I have one kernel in layer 2, will have seen everything, so I can make a decision in layer 3. So layer 3 might be the decision-making time. Hopefully that makes sense to you. So the receptive field, basically, like as you get deeper and deeper into these neural networks, refer to how much of the original input space has this point in the deep layer, how much information has reached it. There's a little bit of a syntactic error here from my slides, but it's basically just a link to where this image comes from. I'll fix it before I post the slides. So most convolutional neural networks are made up of many repeating pieces. You have this convolutional layer, which takes in the number of channels, the number of output channels. So this is the number of kernels you have, the kernel size, the little heights and widths, the stride and the padding. Okay, so and in fact, this is the function that you see in PyTorch, which you can get some information in the documentation linked here. So often you have pooling, like I mentioned earlier, after the convolution, producing this pseudo level of activations, you'll do pooling, like we talked about a moment ago, and is a complete corollary of the pooling we've seen in previous modules. There'll also be a nonlinearity, so just like we've seen in other kinds of neural networks, you'll have a nonlinearity, like a ReLU function. ReLU is very typical. There might be some normalization. You might see a batch norm like we talked about previously. So all of the same kind of concepts we introduced previously, nonlinearities, pooling, normalization, that applies here also. And you can just stack these on top of each other as calls in a sequence like we've seen in previous invocations of PyTorch. Eventually there'll be a classification head. So usually the last layer of all of these blocks of convolutions with all the complexity will just be a simple linear classifier, maybe something like a logistic regression. It'll do some flattening. There may be some extra dense layers. It might just be one layer for a head. It might be a couple of layers, but essentially you have a head on top of everything, and that will do your classification at the end. So this is a kind of a default pattern. You'll have a two-dimensional convolution, pass through ReLU, maybe pass through pooling. That'll lead into a second layer of convolutions, pass through another ReLU, maybe pass through another layer of pooling, eventually pass through pooling at the end, and then that will, like we saw this a moment ago. Okay, so now let's see a worked example for classification, which will basically be the culmination of some of the topics we started off this lecture with, which is like, why are we using CNNs in the first place? So here we're going to use CFAR again, and again we're going to use a multi-layer perceptron. Now it's going to be a baseline. I think we talked a lot about baselines previously, but at one point the multi-layer perceptron was our new and improved model that improved over previous forms of machine learning. Now we're going to compare it against CNNs, which is our new one. We're going to keep things simple. We're going to only do a few epochs. It's going to be a small subset of CFAR 10. So it's going to run quickly in these slides, and for you if you download and run this yourself, but keep that in mind. So there's a lot of code here. I'm not going to walk through all of it. It's going to use PyTorch and Torch Vision. I always find myself doing this. I'm gonna try to not mention every single line. So it's important to remember that you want to move as much as you can to devices that are capable of optimizing machine learning. So we're going to figure out, well, if we have a CUDA card here that allows us to do machine learning in parallel effectively, we'll do that. Otherwise, we'll use our CPU for everything. Here's where we grab the data sets. We're going to download it. We're going to, this is CFAR 10, which comes from Torch Vision's data sets. We'll set our random seed, and we'll just choose indices from the training and tests, so small subsets of these, and then we'll load them into our train loader, which comes from data loader. So data loader is a utility function from PyTorch that allows us to load the data for us to be used for machine learning. We're going to use batch size of 64. We're going to shuffle the data, and so on. So here's our MLP classifier. Nothing really new here. We are going to use a sequence. We're going to use a linear classifier. We're going to use, it's a 32 by 32 inputs in CFAR 10. RGB, so we have 3 channels, and then we have 512 units of output. These are going to be passed through the ReLU nonlinearity, and then this will be passed through a second layer, which will take 512 units of input, and will output 10, indicating the 10 classes we have in CFAR 10. Okay, and we'll define the forward inference, and all of this will run on the device that we identified a moment ago. Now we have our small CNN. So this is essentially the sequence that I kind of just showed a moment ago in text. It's a sequence, so this is a 2-dimensional convolution. It will have 3 channels. It'll take 32 by 32. We only have to mention 32 once here. Its kernel size will be 3. It's going to be square, so the height and width are both 3. Its its padding is going to be 1, so we can move this kernel over the edge of the input image. So this convolution will produce another 32 by 32 active output from that convolution. All of those outputs are going to be passed through a ReLU non-linearity. We're going to do max pooling right away. Its kernel size will be 2, so this will result in a 16 by 16 pseudo image, and then so on. So we have a second convolutional layer, and this will be kernel size 3 again, padding is 1. This is passed through a nonlinearity again. This is passed through a max pooling also. This is another kernel size of 2. And then it'll flatten, and then we have a linear head on the end, which I mentioned a moment ago. And at this point, we've got a 64 by 8 by 8, and then this will be our 10 units for the 10 classes in CFAR10. And again, we push our small CNN to the device. Here's a little helper for training. Again, I don't want to go into too much detail here, but we have to zero out our gradients, which is one of the things we've talked about a lot in PyTorch. Whenever we're accumulating the gradients that we're learning, given our desired outputs. They're helpful for us when we're doing that batch, but we have to zero them out every single time we load a certain batch of data. Here's our data loader. We get our x's, our inputs. We get our y's, our classes. Both of these are going to be stored on device. We have our model. We get our loss function, which just compares the outputs of our neural networks to the desired outputs y. Then we'll push everything back. We'll optimize our weights. This will give us our total loss, which we're going to store. And we'll also store how correct we are down here in our classification. Sorry, so this PREDS basically. I think you know this already. Logits is basically the outputs of these 10 output layers will not all be 1 or 0 respectively. There'll be varieties in those ranges. So we just need to choose which one is the maximum one. This will be our prediction, and the value of that prediction, its index, will be the class, and then we can compare how often we get that class correct. So we have our loss, we have our accuracy, and we'll return both the total loss and the total value of correctness. So this is the training for one epoch. This is our evaluation, which again follows basically the same logic. Here's where we actually use it. We're going to run a little experiment. We're going to use cross entropy loss because we're doing classification. We'll use the atom optimizer, which we've used previously and talked about previously also. We'll have our learning rate, and the number of epochs is only 5 here to keep it simple. Our learning rate is set by hand, and you can optimize this also on your validation data. For the number of epochs we have, of which there's 5 of them here, we'll do a training epoch. We'll evaluate how well we're doing on the test here. So again, I'm playing quick and loose with this. Here, a test would normally be a validation set, but just for the sake of argument, just to have something for you to see. This is what the experiments look like, and we get our outputs of these experiments over all of our epochs. We're going to have one experiment where the model is the multi-layer perceptron, which is a little neural network sequence in Python, in PyTorch. We'll have our CNN, which is another structure in PyTorch. We'll run the same experiment with the same epochs, the same data, and the same learning rates for each of the MLP baseline and the CNN model, and then we'll look at them. So here you can see the outputs of each. The training accuracy goes up and up and up in each of these 2 experiments. The test accuracy seems to fluctuate a little bit for the MLP, and it seems to mostly be going up, but then it sort of peters off a little again at the 5th epoch. Again, things are very simple here, but you can see a little bit of dynamics already in the epochs. Now, how well are we doing at the end? So this here, I'm just counting the number of parameters in my model. I'm producing a single data frame for my 2 models, the number of parameters I'm needing, the final training accuracy of each, the final test accuracy of each, and then I'm just showing you. So here we are. The MLP requires almost 1.6 million parameters, which kind of coincides with the situation we saw at the beginning of this module. At the end, we have a training accuracy of almost 62% and a test accuracy of almost 39%. The CNN, by contrast, only requires 60,000 or so parameters. At the end of training, it gets slightly better. It gets 62.24% accuracy on trained data, but it gets a lot better test accuracy. It's a bit over 50% test accuracy, which again, then, like the generalization is the name of the game, and this CNN seems to be doing far better with far less. I mean, at this point, you might be asking questions of yourself. Is this massive improvement on test accuracy really the result of using these kernels that we've been talking about quite a bit in this module, or is it the result of merely being more efficacious with the number of parameters we're using? We're well familiar by this point with the challenges associated with overfitting, and we know that overfitting comes from a massive amount of parameters. Is this the result of overfitting only, or is it the result also of the fact that we're using CNN architecture with this kernels scanning over layers? That will be left for you to do experiments with, but at this point, at least the CNN structure is vastly improving on what we had previously. This is just a visualization of what we saw over the epochs of training. So the MLP training and tests shown here in solid lines. Training gets better and better. Test doesn't really seem to improve. So it doesn't matter how much training we're doing. Test doesn't seem to do any better than possibly random chance. Actually a bit better than random chance for a 10 class output, but still it doesn't seem to improve over the training process. Whereas with the CNN we get better and better, so the curves trend downwards. The test curve starts better and also trends downwards, but then it kind of picks up at the end. So I mean, you can ask yourself, does the CNN reach better test loss? This should be obvious to you. Is either model clearly overfitting? Or maybe both of them are overfitting, but just to different extents. You can get that kind of information from looking at this graph. I'd like you to answer that question for yourself, if possible, in your notebook. So in summary already, so CNN-based classification is basically kind of like a pre-filter for organizing. It can be used, rather. So we can use a CNN classifier as a sort of filter for organizing our photos in some kind of consumer app. Okay, so maybe our consumer app is just going to be recognizing digits, like in MNIST. Maybe it's recognizing dogs and cats and airplanes and cars, like in CFAR. And then maybe the goal is just getting as accurate as you can with your photo organizer. You'll still want to look at confusion matrices, like how often do these two classes get confused for one another. Maybe top 3 accuracies will be important for some user experience. Maybe you'll have like a photo and then you get a little kind of overlay saying, I think this could be class X, but it could also be class Y. You have a little top 3 accuracy. You want to optimize that for the user experience, so it really depends on how this is being used. But obviously, for sensitive applications like medical imaging or safety-critical robotics, you'll care about things like miss rate. So recall will matter a lot for certain classes. So like cancer detection, you want to avoid missing cancers, obviously. You'll care about calibration. So right now, in the previous examples, we had the logits, like the outputs of our, the 10 outputs of our neural network. We just took the max of those. So whichever output was the highest, we said this neural network is claiming that this input belongs to that particular class. But if the output of the maximum, if the activation of the maximum activation of all the outputs was, say, 0.61, and the second biggest activation was 0.6, is that a big enough difference between those two output neurons to suggest that it's definitely the former and definitely not the latter? So taking into account calibration and considering the confidence or the differences across this output layer matters. You can compare, the uncertainty you get or the entropy. I guess you all know what that means of the outputs compared to accuracy. And then robustness to distribution shift. So you could look at different subsets of your input images. Look at the darker ones, the lighter ones, the ones that are rotated or not, see if there's any shift going on. that has a big effect on the metrics you're looking at. So you have to, again, dig deeper than surface level analysis of metrics. So it is true that CNNs will provide better feature extraction for images than MLPs. So they really do detect things like edges or textures where they're relevant. But the evaluation metric still has to be considered. So it's not like CNNs aren't a silver bullet. Nothing is. Your evaluation is going to have to match the reality of its potential use case. When you're applying CNNs, again, this is this is going to be important. Bias and risk, bias and representation matters in images. Training images may overrepresent some groups and underrepresent others. I might add another citation here. There's a famous example of images of skin lesions on the skin, obviously, and using a CNN-based deep neural network. The original authors of that paper were able to get very good performance on detecting which skin lesions were malignant and which ones were not. And then very quickly some follow-up work came out and said, well, it works very well if the skin is pale, but if you have darker shaded skin, the same architecture doesn't do so well. And that's not really an effect of the architecture. It's not the CNN's fault, so to speak, but it's the CNN plus the empirical environment in which it lives. It's the fault of that. So like if the original authors didn't include enough dark skin data in the data set and they didn't account for it, then that kind of the claims that you might make about the accuracy of this approach would be overblown for certain populations. So again, you might have seen examples. I might have some links here also of image recognizers doing very poorly for certain races. So face recognition was notoriously bad for people of certain East Asian countries. Face recognition performed very badly for them, which means that other people could unlock their phones, for example, using the face biometrics based on architectures like this. Privacy, so images can contain sensitive information like faces, locations, documents, even sometimes in reflections, even sometimes like ancillary data. So if a face is blurred out, but someone's very unique shoes are shown at the bottom of the image, then you can still re-identify them. This is something that I encountered in my previous life. We did a lot of work to try to blur out frames of a video of people's faces and bodies. But if you had, hours and hours of video recorded at say 60 hertz, and you only miss like a few pixels of someone's shoe somewhere within those hours, then you can say, well, the only person in that room at that time wearing a red sneaker is so-and-so, so I know who it is. So privacy is a big challenge. And then even the embeddings that you learn, or the raw images, can still contain implications for user privacy. Deep neural networks can memorize images, or memorize aspects of the data. So sometimes small imperceptible perturbations can fool CNNs. So there's some work, including this one, that shows that you can apply some noise to CNN's output, or the pixels fed into a CNN, so that a CNN will get drastically different results based on images that to you and I will look almost identical. So peppering very particular noise can just totally confuse these image detection systems. So again, over-trusting predictions is always a risk. You always have to be careful, especially in safety-critical systems. There are various mitigations which are beyond the scope of this third-year course, but using diverse data sets, so that would have helped in the first case. Using data sets that include data from diverse populations can help. Auditing the data set curation process, monitoring performance across subgroups. I guess this is very similar to what we've seen previously, but it applies here as well. Anonymizing and securing data is going to be important. But like I mentioned a moment ago, this doesn't always work. Even if you do on-device training or on-device inference, it's possible that even if you blur out an image very carefully, it's possible that those kinds of techniques won't be perfect. So you have to be aware of that. And then take possible precautionary action. I think as much as you can do on device, so if your user data never leaves your device, that's usually a good thing. In fact, I'd recommend it for almost every application you can think of. There is a little bit of extra, this is going a bit beyond this course, but there are techniques where you can add noise to the input or like blur out or try to anonymize the data itself to try to remove personal information from the data. But like I mentioned a moment ago, those methods aren't perfect. So personal information can leak into the model you're learning from a ton of data. There are also other techniques that you can apply to the data. You can add noise, change the model. So you can modify the model with some extra noise added judiciously, so that you kind of filter out information that could be used to re-identify particular people. That also is not perfect, but those two approaches combined can result in a system which is far more privacy preserving. So the latter, the adding noise to the model as opposed to the data, there's various techniques for that, the most popular of which might be something called differential privacy. I might add a link to that also. It's a bit beyond the scope of this class, but I wanted to mention that as well. And again, keeping humans in the loop as much as possible is going to be important. I increasingly think that, I think that some of the idea that AI is going to replace humans, like in the near term, might be overblown in a lot of cases. But I also believe that there's going to be a special sort of new positions for humans that are sort of like model wranglers that understand the kinds of challenges that we're talking about in this class better than the general population, that can have oversight for some of the challenges that we're talking about today. CNNs show up in vision, obviously, so here's some kind of really early papers that are foundational to CNNs being used in computer vision. So image classification, object detection, segmentation. Maybe we'll talk about this in the next module, but sort of identifying, regions of an image in which an object is found, as opposed to classifying a whole image as having something in it. CNNs can also be applied to audio series. So we introduced the idea of convolutions in terms of one-dimensional signals. So because you can pass one-dimensional kernels on one-dimensional signals like speech, and therefore you can do speech recognition on them. So there's a ton of work on convolutional neural networks applied to speech recognition. There's also work by Yoshua Bengio, which would have been good to include here. ECG analysis, so measuring cardiograms. Those are also one-dimensional signals, passing convolutions over them, because the position of your heart rate, or the value of your heart rate over time, or your heart output over time will depend on the context. You can make use of that context by having these kernels. Same idea. You can also have hybrids, so CNN front ends feeding into transformers in massive vision language models are very common, and we're probably going to see this in the next module also. So there's lots of connections to various ways in which these fundamental convolutional blocks, which is what this module is all about, can fit together in unique and interesting ways. So again, to summarize, CNNs kind of bake in some strong assumptions. So we're assuming that nearby pixels kind of change together. So there's locality. So like the value of a particular pixel is closely related to the pixels around it. We also have the assumption that translational equivariance is possible. So if you have small, linear shifts to the pixels in the of the input, whether it's from the camera moving or the objects moving, that shouldn't change the nature of what we're looking at. So the classifier should output the same classes, and the representations shouldn't change too much either. So the features that we're learning should be relatively robust, and the robustness of those features come from this shared weights. So the fact that we have all of these kernels running over all of our images and scanning over our images, detecting horizontal edges, vertical edges, upward turning edges, so on and so on and so on. That robustness comes from these sort of features we're learning from these shared weight kernels. So the kernels are the things learning the important features at every stage. These are what we might call inductive biases. So it works very well for natural images, but it might not always be ideal if the geometry is non-Euclidean. So this is not often the case when we're dealing with photographs in the real world, which we kind of assume to be Euclidean, at least it looks Euclidean from this point of view. But certainly graphs will use another structure. So graph neural networks or graph convolutional neural networks are another class of neural network architecture, which might be more appropriate for non-Euclidean spaces. And also kind of global relationships. Because we're focusing on local shifts to pixels, any kind of long-term relationships will be hard to represent in these local little kernels that we're passing over, an image, especially large images. So therefore, attention might be helpful. So if you're looking at the intermediate representations from stacks of convolutional neural network blocks, you might want to maybe attend or say, well, like the upper left-hand corner and the lower right-hand corner have some kind of correlation happening between them. I want to make use of that correlation. I'm going to attend to both of them at the same time. We're getting ahead of ourselves a little bit. There's a whole section of modules later on in which we'll talk about that. But the way we've defined convolutional neural networks, because of the locality of the kernels, makes the sort of long-term dependencies hard to represent by default. So yeah, again, I guess a tip generally, thinking in terms of what kinds of invariances I'm assuming, or what kind of equivariances I'm assuming, and building into my model. You just have to remember that, okay? So, we started this whole module talking about the fact that there is a sort of equivariance to my vision when I'm moving this keyboard around in it. And that's a safe assumption to make, but is that always the right assumption to make? Maybe if I move a pixel, like the kernel, if I move the keyboard over just a few pixels and I see some kind of nonlinear behavior happening, first of all, I'd have to go lie down to make sure if there's anything wrong with me. But secondly, that might be sort of a nonlinearity in a global scale that I need to account for also. So here's our good old quick checks to make sure you're following the core concepts appropriately. Here are some references. There'll be more before I post the slides. As always, thank you and see you next time.